students, welcome to class. This is Mrs. Brunk, and welcome to Lesson 10-2, Graphing Square Root Functions. And you might have thought that was last lesson. We just did graphing square root functions. Well, today our emphasis is going to be more on looking at transformations and what each element of the equation for a root function does to the parent function. And so we'll be reviewing again the rules of how we transform functions and what that net effect is on the graphs. And so our essential question, which is how we always like to start our lessons, so we know how to focus, is how can you use transformations of a parent square root function to graph functions of the form a times the square root of x minus h plus k, or g of x is equal to the square root of 1 over b times x minus h plus k. So of course those look very familiar to you, I'm sure, because we've used some form or the other of them with rational functions, with quadratic functions, with absolute value functions. And so by now, hopefully you're a transformation expert, and this lesson will make complete sense. But let's start off by first looking at the most basic square root function. And we're going to kind of take a look at, again, that's called the parent function. We're going to be looking at the square root of x in its base position. So y equals the square root of x, or f of x equals the square root of x. So when I think about numbers that I can substitute in for the square root of x, remember I'm very limited on my domain because I'm not allowed to have the radicand be negative. And so the smallest possible value I can put in here is 0, because then I'd be taking the square root of 0. So of course that's 0. I could substitute 1 in, and I'd get 1. Square root of 1 is 1. Notice I'm picking numbers to substitute in that are nice perfect squares. So when I substitute 4 in, I'll get the square root of 4, which is 2. And when I substitute 9 in, I get 3. And so plotting this parent function out, that first point's at 0, 0. The next one's at 1, 1. Then at 4, 2. And then at 9, 3. And we can, again, see that one, basically that reflection of that one side of the parabola, x squared, but over the line y equals x. And so that's the square root of x. That's the parent function for the square root of x. So we've talked a little bit about the domain and what's possible for the domain. And so we know that the domain values have to be values that won't make the radicand negative. So for the parent function, that means it has to be x greater than or equal to 0. So anything 0 and above is fine to substitute in. But what about the range? Well, remember the range, we look at the graph high to low, and you can clearly see that the lowest that this graph ever gets is right here at 0. And then really anything above that's possible. It definitely is growing very slowly. It's going to take a while, but it eventually could possibly be any value for y that's greater than or equal to 0. Now, if we wanted to look at the end behavior of this graph, you can see as we're getting further and further to the right, so in other words, as x is approaching positive infinity, so we know that the function itself is actually approaching positive infinity as well. It's going to take a really, really long time for it to get there because it is still increasing, but it's increasing much slower than it was at the beginning of the graph near 0. Okay, let's go ahead and turn the page. So what I would like to have you do here is take a moment and pause the video. We've studied a lot about transformations. We have explored transformations of quadratic functions, absolute value functions, rational functions, and hopefully it's becoming old hat. And in each one of these examples, A through D, you are given some different transformations of the square root of x, and just going to see if you can make a prediction on each of these, and kind of make that connection to some other kind of transformations we've studied in the past. So go ahead and pause the video now, and let's see how well you do with predicting what each one of these things will do to the square root of x. All right, so thank you for trying those. You may want to take a moment
and pause the video and check out your work. But hopefully these kind of were right in line with what your predictions were. We know that in this first scenario, anything that we're doing underneath the radical sign there will have some sort of horizontal effect, and because we're adding or subtracting, it's going to be a slide left or right or a translation. And just one thing we have to remember with any horizontal slides, that x lies to you. So we always have to kind of anticipate it's going to go the opposite direction. So an x minus 2 would go to the right, whereas an x plus 2 would go to the left. The up and down transformations in B, the vertical stretches and reflections over the x-axis in C, and then again the much less intuitive would be the horizontal stretches and compressions, because remember, whatever that scale factor is really the reciprocal of what x is being multiplied by under that radical. And then if you have a negative there under the radical, that means it's going to be reflecting over the y-axis instead of over the x-axis, so it'll be facing the other direction. Let's continue on the next page.
So in general, there are two different formats for square root functions. And the first
would be if you wanted to describe slides left or right and up or down, and then also a vertical stretch or compression with a reflection over the x-axis. And so each of those letters, H and K and A, represent those same things they've always represented. The H always represents the horizontal slide, K the vertical slide, the A would indicate a vertical stretch or compression, and if it's negative, if A is negative, would mean it's reflecting over the x-axis.
Now the B would describe, over here is going to describe the horizontal stretch or compression, with a negative B indicating a reflection over the y-axis. So these are all very consistent with the things that we've learned about transformation in the past, studying other families of functions. So taking a look at the first example, it says for each of the transformed square root functions, find the transformed reference points and use them to plot the transformation function on the same graph with the parent function. Describe the domain and the range using set notation. Well, example A has been done for us, and you remember this first graph, this parent function here, has some really specific points that will help us as we do transformations. The first point was at 0, 0, is the square root of 0, 0. The next one was at 1, 1, because the square root of 1 is 1. And then the next one being at 4, 2. There's a point right there at 4, 2. We could use that as a reference point. And then, of course, 9, 3 would be on there as well, which is here at the end. So we could use those points as we transform as some reference points. So this first example, we can see that there is a slide to the right 3 units, down 2 units.
There is also a vertical stretch of factor 2. So if we wanted to graph this, and you can see they've already done that, but the first thing we would do is we would identify where that new starting point was. Instead of being at 0, 0, now that point 0, 0 has been moved 3 units to the right and 2 units down, and this is that new point. And so that you could use that slide amount to locate that first point 0, 0. Now normally from that point, as you can see right up here, we would go to the right 1 and up 1, and then to the right 4 and up 2. But now because we're doing a vertical stretch of factor 2, instead if we went right 1, we'd have to go up 2, and that's where this point is. And if we wanted to go right 4, 1, 2, 3, 4, we normally would go up 2, but now we're going to go up twice that, which is 4. 1, 2, 3, 4, and that puts us at that point there. And that gives us enough points to get a nice shape of that graph. So let's go ahead and take a look at example B. So describing that transformation, I can see here that there is a slide 2 units to the right 1 unit up.
There's a horizontal, and because the reciprocal of that 1/2 would be 2, it's actually a horizontal stretch of 2. And also reflection over the y-axis, because that 1/2 is negative. So now to graph that, the first thing we're going to do is use that slide of 2 right and 1 up to locate the new starting point. So I could go 2 to the right and up 1, which would actually put me right there. But remember, I also then have to reflect over the y-axis. So now instead of this being over here on the right-hand side of the y-axis, it's now going to be over on the left-hand side. And it's going to be facing that to the left now. And oops, I'm sorry, that does not make sense. So actually, if you took the graph and reflected it over to the left, but then slid it 2 to the right and 1 up, you're still with your point here, but then the graph's just going to face to the left instead of facing to the right now. So normally we would go 1 to the right, and we would go 1 up. So normally like your point would be right there, but because we did the reflection, we're going to go the opposite way. And now, since it's a horizontal stretch of 2, instead of going 1, we're going to go 2. So this time I'm going to go 2 to the left and up 1 to get that horizontal stretch. To the left, up 1 puts me right there. And now I can see that graph is facing to the left because of that reflection. So I see the slide 2 units right, 1 unit up, the reflection over the y-axis, and the horizontal stretch of factor 2. So if you would take a moment, pause the video, and give number 4 and 5, the your turn questions, a try. You can tune back in and check your answers. Pause the video now. So go ahead and take a moment and compare your description of the transformation to the ones listed, and take a look at your graph and see if it appears to look similar to the one that I've graphed here. Now, one of the things that we need to talk about with these examples that we kind of breezed on by a little bit as we were just focusing on describing the transformation and getting the graph is the domain and range. So we want to talk about the domain and range, and we go back up and look at A. And so when I want to describe the domain of this function, and I'm describing the x value, what you can see is that this x values, there are no x values at all left of 3 in this case. And that's because the x coordinate of that, basically that starting point, is at 3, -2. And so we can't put anything smaller than 3 into that function because it would make the radical negative. And so that means that the x values have to always be greater than or equal to 3, because that would make the radicand 0. Now the range, that range you can tell by just looking at the graph, and you can tell that the lowest that point ever gets to is at -2. So this coordinate right here really represents the 2 main parameters for the domain and the range, like either the lowest value or the highest value. And in this case, it's the lowest value for both. So y would have to be greater than or equal to -2. And that's my range. Now looking at example B, this time when I look at that key point there on the end of the graph, as it's actually, in this case, it might sort of be considered the beginning of the graph since it's going to the left. So that points at 2, 1, because this was a shift 2 to the right and 1 up. And so I know that that domain would have to only include values of x that are going to be less than or equal to 2. And that's because I'm going to put 2 in there. Hold on. And then I'm going to put a number in there. I'm going to subtract 2. But then I'm going to end up multiplying it by a -1/2. And because, so that means I want whatever is in the parentheses to be negative, so that when I multiply it by a -1/2, that becomes positive, so that I can
then take the square root of it. So in this case, x is going to be less than or equal to negative 2. And when I look at that range, looking up and down, I can see that the lowest point that y ever reaches is that y coordinate of that point, and this point right here, and that would be at 1, so y must be greater than or equal to 1, because the graph exists above that. So go ahead and take a moment, pause the video, and see if you can describe the domain and range of the 2 your-turn questions. Pause the video now. So go ahead and check out your domain and range for number 4 and 5. Notice on number 4, this time the range, the y values are always less than or equal to that y coordinate of that key point, and that's because the graph is facing down because of the reflection over the x-axis. Let's go ahead and turn the page. Now this time we want to work in reverse. We want to take the graph as it appears, and we want to write the function to describe it. So looking at example A, the first thing I want to do is I want to identify this point. That point is really important. We saw that that tells us the shift. And so I know that this shift is over 1 and down 2. So it's 1 to the right and down 2. So as I'm kind of filling these things in up in my, my general function, I can see that the h would be 1. So I'm going to have x minus 1. And then I'm going to have the k part will be the minus 2, so it's slid down 2. But this thing obviously has a reflection over the y-axis. And if you look at how the points go, normally, you know, when you go 1 to the right, you'd go 1 up, but now we're going 1, 2 to the left and up 2.
But remember, each one of these little tick marks is a half. You can tell by the scaling. So that's really going 1 to the right, or actually 1 to the left and 1 up. So there really is no horizontal stretch or compression necessarily, but there is a reflection over the y-axis. So there has to be a negative under the radical. And I guess you could write it if you wanted to as negative 1. But the negative is also fine because all that's happening here is it's just being reflected over the y-axis. There's no stretch or compression horizontally. Now looking at this next example, I can see that and identify that initial point there is now this time, and again the scaling is important to look at because it almost messed me up on the last one. The scaling here is negative 2, negative 1. Or the scaling is 1, so this point right here is negative 2, negative 1, and that means I know that this has been slid 2 to the left and 1 down. And so as far as the general function here goes, I know that the h is going to be negative 2, so that's x minus negative 2, which makes x plus 2. And then the k is negative 1. And then we want to see if there's any there's obviously no reflection, but we want to see if there's a vertical stretch or compression. And so I know that for this graph, as I go to the right one, instead of going up 1, which I normally do, I'm going up 1, 2, 3. And that indicates to me that there must be a stretch of factor 3 vertically. So that would give me 3 out in front, 3 square root of x plus 2 minus 1. And I could always put it in my graphing calculator and compare that to the original function square root of x and see that, in fact, that there is that stretch of factor 3 vertically, a slide 2 units left and 1 unit down. And as usual, there are a couple your-turn questions, so please take a moment to pause the video and give number 6 and number 7 a try. Pause the video now. So thanks for giving those 2 a try. Take a moment and check your answers against these answers, and make a note if you have any questions. We can always delve a little deeper into them when I see you in class. Let's go ahead and turn the page. So our final section is going to be on modeling with square root functions. So square root functions that model real-world situations can be used to investigate average rates of change. So average rate of change. Recall that the average rate of change of the function f of x over an interval from x sub 1 to x sub 2 is given
by the average rate of change, f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1, which is really just like saying the slope. It's really like saying y sub 2 minus y sub 1 over, oops, that's supposed to be a 1, over x2 minus x1. But why we call this the rate of change is because we use the term slope when we have a straight path or a line, when there's that consistent rate of change. But clearly on a curve like a square root function, the rate of change is not constant. It sometimes is faster and sometimes tapers off. And, like with this one, it looked like it was growing pretty, steeply. We'll look at the example in a minute, and then it starts to taper off a bit. And so we want to be able to calculate the rate of change between in different intervals of the situation. So it says to use a calculator to evaluate the model at the indicated points and connect the points with a curve to complete the graph of the model. Calculate the average rate of change over the first and last intervals of and explain what the rate of change represents. And so what they want us to do is we're going to do, when we get done with these points, they've already actually generated the points for us, but they wanted us to then take the first interval, which would be these 2 points, and then the last interval, which would be these 2 coordinates, and calculate the rate of change and compare them. So the approximate period t of a pendulum, the time it takes a pendulum to complete one swing, is given in seconds by the formula t is equal to 0.32 times the square root of L, where L is the length of the pendulum in inches. And they ask us to use 2, 4, 6, 8, and 10 for our table. So we went ahead and substituted those coordinates in. We've graphed it over here, and you can kind of see that trend of the graph. And at first it was, the trend was quite steep over this interval right here, which is going to be the first interval that we look at from, actually, I guess I picked the wrong one, because that shouldn't have been this interval here. As far as the first interval, it should have been between 0 and 2. So actually the very first coordinate is, although the way I look at the way that they have it in the textbook, it looks like they do want us to do between 2 and 4. But really the first interval would have been from 0 to 2. So I guess if we wanted to be technically correct, that's what we would be looking at. But they did want us to calculate between 2 and 4, and then between 8 and 10. So I'm going to change this little interval here on the graph. So that means I want to actually calculate between these values, so from 2 to 4, and then compare that to the rate of change between 8 and 10. It definitely looks like it's going to be a little steeper between 2 and 4, so the rate of change should be a little bigger than it is between 8 and 10. So we can just take those coordinates, we'll calculate the rate of change. So I'm going to do the y2 minus y1. For this interval would be the 0.64 minus the 0.45. And then on the denominator, the difference in the x's will be 4 minus 2. So that gives me a 0.19. And on the denominator, I think that's 0.19. And then on the denominator, it's 2. So 0.19 divided by 2 is 0.095. So that's 0.095, and the rate of change is seconds per inch. So that's in seconds per inch. Now if we do the rate of change over that other interval, now we're going to be using these coordinates, the 1.01, which is the y coordinate of the second point, and then the y coordinate of that first point is 0.91, and then the x coordinate of the second point is 10, and the x coordinate of the first point is 8. So that numerator, if we subtract 0.91 from 1.01, we get 1.01, and then the 8 minus the 10 is 2. Divide those two, and we get a rate of change of 0.05. So again, the unit on this is seconds per inch. So about 5/100ths of a second per inch, versus in that first interval, it was 95 thousandths of a second per inch. So almost 1/10. So what we're going to do is we're going to hold off on this next example. We're going to have this be a in-class example, and that'll kind of kick us off for the next class, and we can talk more about transformation of square root functions. Thanks for coming to class.